So this video is on the pH scale. There's two little background pieces of information that are critical to understanding the pH scale. One of them involves something called logarithms, and the only type of logarithm you use here is called a base 10 logarithm, and the math is really easy. You will not need to break out your calculator at all, period. If you do, you don't understand it, because the math that the Regents expects you to do here should not involve a calculator. All right, let's talk about what a logarithm is in the simplest terms. So if somebody said, what's a log of 10, and you're using the base 10, they're basically saying you 10 to what power is 10. So, well, 10 to what power is 10? 1. If they say the log of 100, they're saying 10 to what power is 100. So in this case, what is x equal to? Well, 10 to what power is 100 is pretty easy. That's 2. If you're doing the log of 1,000, you're saying 10 to what power is 1,000? And the answer for that is 3. Now, we're not going to be dealing with big numbers when we do this, what's called like logarithmic scale. We're going to be dealing with smaller numbers because we're going to be dealing with concentrations of hydroniums and hydroxides. And their concentration will be things like 0.1 and 0.01 and 0.001. So we have to be able to take logs of those and do them in our head. And they're not very difficult either. Okay? So what is a log base 10 of 0.1? So 10 to what power is 0.1? Well, don't forget what 0.1 is. 0.1 is just 1 over 10, isn't it? Which is the same as 10 to the minus 1, isn't it? Right? 10 to the minus 1 is 1/10. So the log of 0.1, okay, is just negative 1. The log of 0.01 is saying, that's the log, 100th or equal, right? So 10 to what power is 100th? Well, that's 1 over 10 to the second power, which is just equal to 10 to the minus 2, isn't it? So the log of 0.01 would be negative 2. The log of 0.001 would be negative 3, and the log of like 0.00001 would be like minus 6, I think. Not sure how many zeros I said there. Really, really easy, though. Okay? Now, you could be given different numbers if you take an AP, like they can ask you what the log of 0.012 is, but you know what? Then you break out your calculator. Okay? But you're not going to see me doing that, and you're certainly not going to see on the Regents. So let's move forward with this. Okay, other piece of background is about water and what's called the KW of water. Now, here's the thing. No matter what else is in the water, there's something true about water, and this is why these equilibrium constants are so useful. No matter whether you have acid or base, okay, the equilibrium expression for the water will always be the same. See, when water bangs into other water molecules in pure water with nothing else in it, every once in a while you get an H3O plus. And you get an OH minus. Basically, one of the waters lost its hydrogen and it was picked up by another water. So for every two water molecules that bang into each other, you get one hydronium and one hydroxide. Sometimes they'll write this way as just H plus and OH minus. Now, the important thing here is these guys are AQ. AQ, AQ, AQ. And the important thing is the equilibrium expression. Because liquids are never put in equilibrium expressions, this has no denominator. It is merely H3O plus times OH minus. And at 25 degrees Celsius, which is normal room temperature, okay, not considered standard temperature, but a lot of work we do in the lab is at that temperature because that's like room temperature. It's like 78 degrees or something like that. All right, that is equal to 10 to the minus 14. Now that will vary at different temperatures, but at 25 degrees, which is when all the experiments are done in the Regents, the KW is 10 to the minus 14. And that leads up to some really easy math and an understanding what the pH scale actually is. So, since the H plus and the OH minus are going to be the same, because for every hydronium you make, you're going to make one hydroxide in pure water, then you should understand that the H plus times the OH minus concentration will be equal to 10 to the minus 14. But they're both the same number, so we can say they're both X. And so then we can go, oh, x squared is equal to 10 to the minus 14, because this is x and this is x, and they are the same in pure water. And then we can do a little square rooting. We can square root this, and we can square root that. And when we do that, we get that x is equal to 10 to the minus 7. Now, what I really want you to notice here is this 10 to the minus 14 is 10 to the minus 7. Sounds pH scaly, doesn't it? Like 7 is the neutral. 7 is neutral, isn't it? 14 is the high end of the scale, usually, right? Well, that's not an accident, because the scale is a logarithmic scale. All right, so what is the pH? Well, the pH is just this. It is the negative log of the H plus concentration. That's all it is. Now, the beauty of this is if you log 10 to the minus 7, you get negative 7. But if you negate this, you get positive 7. So when in pure water, the reason why it's neutral is because the negative log of the H plus, because this is equal to the H plus concentration. It's also equal to hydroxide concentration, right? So I should say equal. But we're doing the pH first. So the idea is that the pH is pH is basically is equal to the negative log of the H plus concentration. There's also something called pOH, which is just the negative log of the OH minus concentration. Now watch how easy this works out. Ready? The H plus concentration times the OH minus concentration is always equal to 10 to the minus 14. Now, so if let's say if the pH was like if this was 10 to the minus 7, then this was 10 to the minus 7 too, wasn't it? Which means the pOH is also 7. Now notice this is 7, this is 7. If you add these two numbers together, you get 14. And that's the beauty of it. The pH plus the pOH will always add up to the number 14. The H plus and the hydronium hydroxide concentration will always multiply out to 10 to the minus 14. And if you just take the negative log of the H plus, that gives you the pH. If you take the negative log of the OH minus concentration, that gives you the pOH. If you take the if you take the pH and you go like this, 10 to the negative pH, that gives you the concentration. So if the pH is 7, right? If the pH is 7, then the concentration is 10 to the minus 7, right? And 10 to the minus pOH would go on this line. Let me show you how this works, because it's really super easy, and there's just a pattern. I'm going to do like 2 of these real fast, okay? And so let's say I tell you that the pH is equal to 3. Well, then the H plus concentration is equal to 10 to the minus 3, which is 0.001, by the way. They're the same thing. They're equal. Okay? The pOH is equal to 11, because 3 plus 11 is 14, and the OH minus concentration is 10 to the minus 11. Now notice, obviously, when we add an acid to the water, the pH actually goes down, because the pH of 3 is more acidic, because 10 to the minus 3 is a bigger value than 10 to the minus 7. And as the H plus concentration goes up, the hydroxide concentration goes down. They have the indirect relationship, because it always multiplies out to the same number, 10 to the minus 14. Now, if the H plus is bigger, the hydroxide has to get smaller to multiply out to the same number. So if I were to, let's say, have a very high pH, which I'm going to erase all this now and do it, let's say the pH was 10. Right? Now, if the pH is equal to 10, right, that means the H plus concentration is equal to 10 to the minus 10 molar. That's not a lot of hydroniums, right? But watch how this plays out. Now, a pH of 10 was basic, wasn't it? Why is it basic? Because when it's basic, there's more hydroxides than hydroniums. So if this is the pH, then the pOH is equal to 4, which means the OH minus concentration is equal to 10 to the minus 4. And note, this is a larger amount, right? So as the pH gets higher, right, it gets basic because there's actually less hydroniums and more hydroxides. And you can do this with anything if you want. I'm just going to do one more because we don't want to run out of time here. But let's imagine, let's say the pOH was equal to 9. Well, then the pH is going to be equal to 5. Which means, now, at this point, since the pH is 5, it's acidic, correct? So since it's acidic, the H plus concentration should be higher than the hydroxide. So what's the H plus concentration equal to? It's equal to 10 to the minus 5. The OH minus is equal to 10 to the minus 9. This is a bigger number than this. It's 1,000 times bigger. Or 10,000 times, sorry. Okay, next slide. So let's just take a look and make sure we understand what happens when we change things on the pH scale. So let's say the H plus concentration is 10 to the minus 7, and the OH minus concentration is also 10 to the minus 7. If the H plus concentration is 10 to the minus 14, then the concentration of OH minus is going to be 10 to the 0, because they multiply out to 10 to the minus 14. Right? Remember, you add exponents. It's not like 0 times 10 to the minus 14 is like 1 times 10 to the minus 14. It's still 10 to the minus 14, right? If the H plus concentration is 0.1 or 10 to the minus 1, the OH minus concentration is 10 to the minus 13. Now what you really want to understand is what it means to move a few notches on the scale. So if I'm going in this direction here, every time I move one notch, okay, I change by a factor of 10. If I move 2 notches, it's 100. 3 notches, 1,000. That's why it's a logarithmic scale. So let's say I go from a pH of, let's say, 3 to a pH of let's say, 6. Well, let's look at that. The concentration of the H plus is 10 to the minus 3, and it's going to 10 to the minus 6. What's the difference between these two? Well, right, this number here is 1,000 times smaller than this number. Right? So going this direction here, I'm sorry, okay, 10 to the minus 6 is 1,000 times. So when you go from 10 to the minus 3 to 10 to the minus 6, the H plus concentration decreases by a factor of 1,000. It gets 1,000 times less acidic. At the same time, the OH minus concentration is going from 10 to the minus 11 to 10 to the minus 8. And 10 to the minus 8 is 1,000 times greater. So that when we do that change from 3 to 6, the H plus goes down by a factor of 1,000, and the OH minus goes up by a factor of 1,000. There's 1,000 times more higher concentration of hydroxides when we move 3 spots. If you move 2 spots, everything changes by 100. So for example, right, what would happen if the pH changes from 3 to 5? Now make sure that when you increase the pH, it's becoming less acidic. We know that, right? And really what it's saying to you is the H plus concentration is going from 10 to the minus 3 to 10 to the minus 5. So what's happening to the hydrogen ion concentration? Well, this is obviously smaller, right? So the H plus concentration is decreasing by a factor of 10 to the second power. That's the difference between those two, which is basically saying it's decreasing, it's 100 times smaller. At the same time, the OH minus concentration is doing the opposite. It's increasing by a factor of 10 to the second power. So it's getting 100 times greater. Let's say we're going from a pH of 11 to 8. Now, in that case, we're actually getting more acidic. The H plus concentration is going from 10 to the minus 11 to 10 to the minus 8. The difference in those two exponents is 3, right? So what's happening is it's getting 1,000 times more acidic. So the H plus is going up, okay, by a factor of 1,000. And the OH minus is going down by a factor of 10 to the third power. It's going to be 1,000 times less. Hope that video helps. Summary, okay, just going backwards in the thing, okay. This diagram right here is really just the whole summary that you really need to know. They're never going to ask you about oil ionization of water or ask you about logarithms. They just want you to be able to do this math right here, and they really want you to be able to handle problems like this. They want you to be able to say how the hydrogen ion or the hydroxide ion concentration changes when you change pH on the scale, and make sure it's going up by a factor of 10 to the something or down by a factor of 10 to the something.